error analysis. And there are many things to be discussed in error analysis. I will get into the statistical part of the error analysis. First, we will take certain definitions on error. So what are the different kinds of error? The first one is systematic error. So what is systematic error? It is a reproducible inaccuracy introduced by faulty equipment or calibrations or technology. Okay. Then the second one is random error. This is indefiniteness of result introduced, finite precision of measurements or statistical variation. Measure of fluctuations after repeated experimentation. In fact, the statistics will handle this random error. Okay. If there is a systematic error in the measurement, it should be solved not by this mathematical or statistical procedure. It must solve physically. Okay. The next one is uncertainty. That is the magnitude of error that is estimated to have been made in determination of results. Then accuracy. Accuracy and precision. Accuracy measure of how close the result of an experiment comes to the true value. But precision is measure of how carefully the result is determined without reference to a true value. Okay, measure to a true value. Then, this picture shows the difference between accuracy and precision. The first one, which is accurate and precise, because this is the target value and all the points distributed within that or in the neighborhood of that one. So this is the case of both accurate and precision. And here you can see the values are clustered at somewhere without much variation, but it is much away from the central value. So this is the case of precision, but there is no accuracy. Okay, the values are not at the target, but there is no much scattering of the measurements. So the precision is there, but there is no accuracy. And this is the case, the accurate but not precise, because it is around the target value, but the values are highly scattered. So the precision is less, but there is accuracy. This is the case which is neither accurate nor precise. Okay, which is scattered somewhere. Okay, the values are much scattered and it is not at the target point. So this is the relation between accuracy and precision. If we measure something, we always expect accurate and precise measurements. Okay, and this accuracy and precision depended on many factors, the systematical factors and the random factors. Okay. And by doing certain analysis, we try to estimate the random error. Then there is another term which is there are also different situations: single experiment or single measurement experiment and a repeated measure experiment. If there is a single measure, the absolute error is the measured value minus true value once the true value is known. Okay. So in the case of single measurement, you can find out the absolute error only if the true value is given, true value is known. Then its relative error is always defined as the absolute error that is expressed in percentage, the absolute error divided by the measured value into 100. Okay, or how much is the error? Okay, with respect to the in repeated measures, suppose there are n measurements, the absolute error is nothing but the mean deviation. Or the average used in the error analysis. The first one is mean deviation, which is nothing but the mean of absolute deviations. Okay, so you take each measurement and first you find out an expected true value. The expected true value is the arithmetic mean. And take deviation of all values from arithmetic mean, that should be absolute, okay, without sign. And then take the sum of that divided by the number of observation, that is called mean deviation. So this is the absolute error estimated in the case of multiple measurements or repeated measurements. Another measure we use in error analysis is standard deviation. The standard deviation is usually defined as 1 by n sigma 1 to n xi minus x bar whole square. But here I given it as 1 by n minus 1 sigma 1 to n xi minus x bar square because here we use an unbiased estimate of the standard deviation. So it is better to use this formula 1 by n minus 1 sigma xi minus x bar the whole squared instead of 1 by n sigma xi minus x bar the whole square. Because 1 by n sigma xi minus x bar the whole squared is not an unbiased estimate. The unbiased estimate is 1 by n minus 1 sigma xi minus x bar the whole square. Then standard error is another measure. It is a measure of the estimate of mean. Okay. Estimate. It is the measure of estimate. So the physical meaning is different. Standard deviation is a scattering measure of the values, observed values. It is a scattering measure of the observed values. But standard error is a scattering measure of the estimate. So you should understand the difference between these two. Okay. Standard deviation is a scattering measure of the observed values. But standard error is a scattering measure of the estimate. So in the case of arithmetic mean, the standard error of arithmetic mean is sigma divided by root n. Sigma divided by root n. That is the standard deviation divided by square root of the number of observations. So these are the three measures we use, okay, for computing the error in error analysis. And these three measures will be used in different scenarios, in different situations. So we will explore that. And in this case, also the relative error is defined as absolute error into 100 divided by arithmetic mean, because the arithmetic mean is the estimated true value, the estimated true value. So if there are multiple measurements, you can estimate the true value by taking the arithmetic mean. But if there is a single value, there is no possibility of estimating that value, and then you need a true value. Another important point in error analysis is if you take more number of measurements, so your error analysis will be more accurate because of this large sample property in statistics. Okay, if you get a large number of observations, it will be consistent, unbiased. Okay, so the large number of observations are there, then definitely the estimate will be very much close to the true value if there is no systematic error. Okay, and what is the significance of statistics in this case? So in fact, you can write it as a model. A measured value is equal to the true value plus systematic error plus random error. If you remember the previous session, you can compare this one with the previous session. Okay. There also we have taken the dependent variable is a function of independent variable plus, which includes the systematic error and random error, which we taken together. Okay. And the probability distribution of random error plays the role of statistical error analysis. So the concept of statistical error analysis lies on the distribution of the random error. Then the distribution of the error time may be any distribution. It may be Poisson distribution or normal distribution, etc. In the case of small sample, the distribution may differ, but in the case of large sample, all this distribution converges to the normal distribution. Okay. So use large sample theory. If the number of repetitions of the experiment is large, the random errors can be approximated to the normal distribution. So usually we use the properties of normal distribution in error analysis. And let us analyze the properties of normal distribution. And this is the mean value of the normal distribution. And sigma is the standard deviation. If you take the interval on sigma, that is mean minus sigma to mean plus sigma, there are 68.26% of observation. The meaning is, if you take on observation from a normal distribution, the chance of that lies in the interval mean minus standard deviation, mean plus standard deviation will be 0.6826. This is the physical meaning. If you take on observation at random from a normal distribution, the probability that it falls in the interval mu minus sigma, mu plus sigma, that is mean minus standard deviation, mean plus standard deviation is equal to 0.6826. Similarly, this is called 1 sigma interval. Then if you take 2 sigma interval, that is mu minus 2 sigma and mu plus 2 sigma, or mean minus 2 into standard deviation, mean plus 2 into standard deviation. There the total area comes 95.44%. Means if you take on observation at random from a normal distribution, the chance of that observation lies in the interval mu minus 2 sigma, mu plus 2 sigma is 0.9544. And the last one, it is 3 sigma interval, mu minus 2 sigma, mu plus 3 sigma. Within that interval, 99.73% of the observation lies. So that means if you take an observation at random from a normal distribution, the chance of it falls in between mu minus 3 sigma and mu plus 3 sigma is 0.9973. The chance of it come below minus 3 sigma, mu minus 3 sigma is 0.0014, and it for the 0.0014, and it go beyond 3 sigma is 0.0014. Okay, so these are the properties of area property of normal distribution, and we make use of this area property in error analysis. So please remember, this analysis will be true only if the error follows normal distribution. Then errors may not be exactly normal distribution. Usually it will follow normal distribution when the sample size is that much, or it may be some 5 or 6 measurements if there will not be any problem. But if you take 2 observation, it may not follow like this. And if there is systematic error, definitely it may not be normal distribution. Then even if the distribution is skewed and there is no systematic error, if you take a large means it is some beyond 30 or something number of measurements, and it will follow normal distribution. It is an approximation. Then the range of new observation, experimental error. If you compute the experimental error, the mean plus or minus standard deviation is the range within the chance of a new observation falls is 68%. Okay. Then how do you find out this one? If you have the measurement, find out the mean value and their standard deviation. But remember, the standard deviation to be computed by the formula square root of 1 by n minus 1 sigma xi minus x bar the whole square. That is the unbiased estimate. Because here, this is not the population mean or population standard deviation. This is only a random number of observations. Okay. And also remember, this is the probability of coming a new observation, not the mean value. Okay. And mean plus or minus 2 standard deviation is the range within the chance of a new observation falls in 95%. Okay. And mean plus or minus 3 standard deviation is the range within the chance of a new observation falls is 99.73%. Okay. So these are the property regarding experimental error by assuming the errors follows normal distribution. Okay. And we make use of this idea to make decision about this error. Here it is experimental error. And there is another term which is called probable error. Then what is probable error? Probable error is defined as an interval, or which is defined as 0.6745 into standard deviation for a single observation, for a new observation, okay, for a future observation. And what it means? The mean plus or minus the probable error is the interval in which a 50% chance a new observation falls. This is the meaning of probable error. So I discussed two types of error. The first one is experimental error, that is expressed as mean plus or minus standard deviation with a different multiplier, and depends on the multiplier, the chance of coming a new observation in the interval will vary. But in the case of probable error, it is just a constant or a multiplier of standard deviation, and the multiplier is 0.6745. And it ensures the chance of 50% a new observation falls in the interval mean plus or minus probable error. Okay. So anybody have any doubt regarding the distinction between this experimental error and probable error?
No, sir. Please continue.
Okay. Then range of new mean value. So till I discussed about the possibility of coming a new observation in a particular interval. But now we examine what is the chance of getting a new mean value. In the case of experimental error, mean plus or minus standard error. You see the standard error, because standard error is a scattering measure of the arithmetic mean. Okay. So in the previous case, we mentioned about the chance of getting a single observation, a new observation. So standard deviation is a measure of the scattering measure of the observed values. It is something about the observation. But standard error is a measure of the estimate. It is a scattering measure of the estimate. So this range will ensure the chance of coming a new mean value. So the chance of coming a new mean value within the interval mean minus standard error and mean plus standard error, which is already defined, sigma divided by root n. That means you can divide the standard deviation with the square root of the number of observations, and which is also 0.68%. And in 2 standard error limit, it will be 95%, and 3 standard error, sorry, this is not standard deviation, 3 standard error is the range within the chance of a new mean value falls in 99.73%. So this is the way we use standard deviation and standard error in expressing the errors. Okay. So here we can compute the errors. Okay. So error is it is a measure of uncertainty, and that will be expressed in either in terms of standard deviation or standard error. So we have been used 3 measures: mean deviation, standard deviation, and that standard error. Mean deviation will be used for absolute measure, and in the case of repeated measurements. But standard deviation will be used for repeated measurements, but it says something about a new observation. But standard error will be computed from the multiple observations. So please, 1 minute, please hold on a minute. Hello.
Yes, sir.
Okay, then, yeah. So these are the properties of standard deviation and the standard error. Then the probable error in the case of new mean value is 0.6745 into standard error. You see the difference between this one and the previous one. Here we compute the probable error by just multiplying this 0.6745 with the standard deviation. And where we should multiply it with the standard deviation, if you are just computing the chance of getting a new observation, okay? But if you have to make inference about the mean value, okay, you should compute it with the standard error. So then this interval, mean plus or minus probable error, is the interval in which a 50% chance a new mean value falls in the interval, or falls, okay? And another important term is called the reliable error. The reliable error is a range within one reliable error on either side of the mean will include 90% of the data false. Okay. So in order to get this one, you have to multiply the standard deviation with the 1.6949. This is called reliable error. And to get a new mean value, it will be 1.6949 into standard error. Okay. And if there is any doubt regarding this one, because I explained many measures, many error measures. So if anybody have any confusion regarding this or any question, or shall I explain anything again? Any question?
Sir, I think there are no questions. Please continue, sir.
Okay, I think everybody is familiar with all these things. So then why I don't know what is the need of this session. Okay, if nobody has no question, okay, then fine. Okay, then the relative uncertainty is the absolute value of the ratio of uncertainty to the measured value. Okay, and how do you measure the uncertainty? Uncertainty can be taken as it can be taken as a measure of the mean average deviation or standard deviation or standard error accordingly. Okay, so nothing but if you predict that interval, the interval will have two components. One component is an uncertainty measure, other is a measured value. If you take the ratio of this uncertainty component to the measured value, that will be called relative uncertainty. Okay, then there is another term, discrepancy. The discrepancy is if a theory expects to predict an expected value xt, and the discrepancy delta is defined as the absolute value of the mean minus xt. Okay, and if delta is less than the standard error, then we can say that the measurement will be within the experimental error. That means the expected experimental error. But if delta is greater than standard error, it is an indication of systematic error. Then you have to check the theory and experiment carefully and do the necessary modifications wherever it required. Okay. So this is the analysis which will to be done to find out any discrepancy. You have to find out two measures. That is, one is the delta measure, discrepancy measure, which is absolute value of mean minus the target value. Okay, expected value. Since if the expected value is given, then if delta is less than standard error, then it will be within the experimental error. If delta is greater than standard error, it is an indication of systematic error. So that means it is not only a random error. Okay. Then check the theory and experiment carefully and do the necessary modifications. Now, the higher level error analysis is not only regarding the measurement of values. We can do the error analysis for relationships also. Okay. For example, suppose there are two variables x and y, and there is an established relationship between X and Y, and we can prove it experimentally. So in any modeling, there are two ways to establish the relationship. One, the theoretical side. Second is the experimental side. Never the experiment value exactly match with the theory. Okay. In fact, there is no perfect relationship. Okay. Because there is a chance of uncertainty. It may be due to the measurement error or something else. If it is influenced only by the measurement error, or that is due to random factors, okay, natural factors, then we call it is, if there is only a natural factor, we call it is a random factor. The variation is only due to the random factor, then we can find out the value, we can remove that value, or we can estimate the effect of the random factor. But if there are certain systematic components, it is not easy as this. Okay. So, suppose a theory says that these variables are related like this, and we try to prove it empirically. We take the measurement of values X and Y, and we estimate it by the principle of least squares, or you can do it maximum likelihood, etc. There are different procedures. And by using this principle and procedures, you can compute the values of A and B. As I mentioned in the case of regression, you can estimate both the values of the parameters as well as the standard error. So then you make use of the previous concepts in regression in this relationship. If you have the estimate and the standard error, you can interpret the precision or the accuracy of the relationship in terms of the confidence interval. So by testing the significance of the model, we can ensure the accuracy and precision of the model that I given in the last session. For example, I constructed a multiple linear regression model, and analysis of variance is used to make the relationship, to construct the relationship, to test the relationship, sorry. And so also corresponding to each parameter, computed their estimated value and the standard error, and we can build a confidence interval for each parameter. Okay. So once you do all these things, you will get the idea about which parameter deviate more, which one is the more consistent, etc. All this information will be available. So you can use statistical procedures both in measurements and relationships or modeling. So the principle is, sometimes we will have theoretical relationship or theory, or in general it is theory, whatever be the subject, even in mathematics or statistics, etc. We may have the theory, and theory may not be useful as it is, because a theory will be useful only when we can identify an instance. Okay. That is why in statistics and mathematics there are several theories they are not using right now. But the theory is not wrong. We assume that, or we proved that the theory is correct. But right now there is no practical use because we could not find out an instance for that. But once you find out the instance, then the theory will be useful. Okay. And again there is a problem. Even if this theory is exact, the empirical, if you try to prove it empirically, there may be a mismatch, slight mismatch. So if that mismatch is due to a random fluctuation, then there will be no problem. But apart from this random fluctuation, something else is influencing the relationship, then you have to check out the theory also, because the theory may be wrong. Okay? This is the principle I mentioned earlier in the case of discrepancy analysis. Okay. If that assumption or that condition get violated, it indicates there is systematic error. And the question is why there is systematic error. The systematic error observed may not be due to the measurement alone. It may be in the theory also. So we have to check out both the theory and the empirical side and identify the problem. So this is the principle, or this is the way we usually modify the theories. Okay, because till we observe empirically, we don't know the real behavior of that one. So this is true everywhere. Okay, there are several theories or several models which is theoretically explained, but we failed to find out an instance in reality. For example, suppose a model or a theory is constructed some 50 years back. At that time, it may not have any instance or any empirical. It could not find out any empirical evidence. But after 50 years or 30 years or 50 years, we may be able to identify, or we may be able to find out an empirical example. Okay, and the research also like that. This is the relationship, the theoretical research and empirical research. In the case of empirical side, always there will be some source of error. But we are looking at whether this error is due to natural factors or not. In all these statistical modeling, the principle is like this. That is why in simple linear regression model, we constructed the model as y equal to ax plus b plus epsilon. Where epsilon is a random term, we assume that it is a factor. It constitutes only the natural sources. Okay, natural source of error. So what is the principle of testing a hypothesis? In testing a hypothesis also, we check whether the variation observed is due to the random fluctuations or not. If that variation is observed due to random fluctuations alone, we say that it is significant. Okay? If that variation is beyond these random fluctuations, then we say that it is not significant because inconsistent. Because that value is not consistent. So very interesting thing is, suppose you take the examples of correlation. Suppose you get a correlation in one case as 0.3 and in another case it is 0.8. Usually the people will say that, okay, in the case of 0.8 there is a high positive correlation and the 0.3 the correlation is less. But if you go for a statistical test, sometimes the correlation 0.3 may be significant and the correlation 0.8 may be insignificant. Okay. So then the people will wonder why this happened, because the correlation 0.8 correlation is not significant but 0.3 is significant. Okay. So the important role played by the standard error. The standard error plays an important role in interpreting the consistency of the estimate. The standard error is very high. What is the interpretation? Your estimate of 0.8 is not reliable. But suppose the case of 0.3, which is highly consistent, we can say that that correlation, whatever observed, which is consistent. So we call it is significant. Okay. So in all these inferential techniques, standard error of the estimate plays an important role. In this error analysis also, the standard error is very important. It is a measure of uncertainty. And then we make use of the results of that normal distribution and we can interpret or we can analyze the error. Okay, these are the topics I have to discuss about error analysis. And if you have time to discuss or anybody have any doubts regarding the last 4 sessions, we will discuss it.
participants, if any queries, we can have an interaction with our resource person. Please come forward.